Here's an activity that our statistics classes did to understand sampling distributions. Activities like this are referenced in several books like The Practice of Statistics and Activity-Based Statistics. Step 1. Collect a lot of pennies. Put them in a bin and mix them well. Then, have each student, one at a time, select one penny and note the year of that penny. Make a histogram that shows the distribution of the pennies. Calculate the mean and standard deviation of your distribution. Here's what our 60 data points look like. At first glance, it looks like the distribution is a little left skewed with some gaps. The mean turns out to be around 1993. Again, take a sample of pennies, but this time randomly choose 5 pennies and calculate the mean year of the sample of pennies. Make a histogram of the distribution, making sure to keep that x-axis the same as the first histogram. Calculate the mean and standard deviation. Here's our data for our 60 students. The spread in this graph has been greatly reduced. In the first graph, we had pennies from 1962 to 2015, but this time with 5 pennies, their average will be less extreme, so the range of values for our students is from 1978 to 2008. Have a class take data again, but this time with a sample size of 10 pennies. Graph your data and calculate the mean and standard deviation for your distribution. Our 60 samples for n equals 10 has tightened up a bit, with the majority of values clustering between 1989 and 1999. There looks to be one outlier sample here that had a 10 penny average of 1974. Finally, have students randomly pick 20 pennies and calculate the same measurements and graph the histogram. Here's our class data. What's happening here? The distributions are becoming less spread out as the sample size increases from 1, 5, 10, and finally 20. Having a larger sample size gives more information from each sample, so the measurements of the mean of all the pennies will be more precise and vary less.
A true sampling distribution is the distribution of values taken by the statistic in all possible samples of the same size from the same population. Because we have a large amount of pennies, finding the mean age of pennies for even a small sample size would take a long time. So we perform a simulated or estimated sampling distribution. That is what these graphs are, experimental sampling distributions. Here are the 2 final takeaways. Number 1 is, as the sample size increases, the spread of a sampling distribution decreases. The larger the sample, the more information one gets, the more precise the statistic gets. And number 2, the central limit theorem, which states that regardless of the shape of a population distribution, uniform, skewed left or right or normal, when n is large, which is typically greater than 30, the sampling distribution of the sample mean is approximately normal.
Now, students are usually able to get the larger sample size, less variability thing, but what's hard to understand is the picture of a sampling distribution. The histograms that we had can be a little misleading because we usually do a histogram bar as a measurement of a singular item. But in the case of a sampling distribution, these bars are actually measurements of many samples. It might be helpful to have your class populate a big grid like we just did here of X bars so they see that the distribution is a distribution of samples, a sampling distribution. Thanks to Josh Tabor, Ben Schmidt, Ian McInerney, and Jeff Tillinghast, and the Practice of Statistics and Activity-Based Statistics.